So we said that there were many technologies which actually play an important role in the development of additive manufacturing. Without these technologies, we cannot invent, construct such additive manufacturing machinery. We said that computers are highly important. We use them for slicing. We use them for designing our parts in CAD software. We use computers to control our machines. We use for communication between the printers, machines, and the users. And we also use them for integrating our system. This was a kind of a diagram showing the machine, the additive manufacturing machines. At the center of this diagram, we have a process controller. This is mostly microcontroller sometimes and real-time computer. So it gathers information from the sensors. It actuates most of the time the motors, the heaters, and it also has a communication with the user interface, and which is usually on a special host PC. And in that host PC, users do some settings, import their models, decide on some specific parameters, and then transfer these actual generated commands to process controller. Then this process controller will take care of the commands and do the fabrication. And this one is the user interface is sometimes connected to the internet or Wi-Fi or your local area network so that you have access to the information on your machine. We said that CAD technology is actually evolved from just being a simple design software with the help of actually CAM software. There were some needs of CAM software. This actually increased the development of, increased speed of development in the CAD systems. And we said that in the early additive manufacturing applications had some problems with the available CAD software since they didn't have actually proper representation of the surfaces. Once we do the STL conversion or triangulation, we had some empty or missing faces, missing, let's say, triangles, and this created real problems, real difficulties while doing slicing, while generating interior structures, interior, let's say, infill patterns or support structures. So that's why additive manufacturing also pushed CAD software to high levels. And now these days, we don't have much problems. These are the complexity of the problems are actually decreased. And we have many CAD software. We can use any of them. There are even online CAD software. I asked you to name some of the online CAD software, but none of you mentioned. I said that we have Tinkercad, but I don't know any other online software. And these days, we have many improvements in the CAD software. They are more realistic. They have better user interfaces. They have engineering components, engineering tools. You can perform analysis, finite element analysis for the given configurations. We can do many operations in a smaller time. The speed is much better with the convention, not with the novel CAD systems. And the accuracy of your models, the designs are much better. You can easily design complicated parts. What about slicing? And if you don't use a special, let's say, CAM software, we said that you can do it on the CAD side, and this is called direct slicing. And this is much better. I mentioned that I don't like STL files, no to STL. Once you do the STL conversion, you will lose many information. It's an approximation. So we prefer to do direct slicing. But the problem was, do you remember the problem? I don't know. In direct slicing, you need to write post-process for all types of additive manufacturing machinery. But if you convert it to STL, then you don't need to do it. Most of the CAM software of different AM machines accepts STL files. And we said that this and de facto standard, which is not formally a standard, but people are using it about 99% of the time, and that's why we call it as a de facto standard. This was an example of a part of an STL file, a triangle. This 7 actually lines are representing a triangle in the STL file. The vertices, their coordinates, and the coordinates, actually the values of the unit normal vector. Here's an example. And we said that we don't like STL files. They have many problems, and we will be talking about these issues in upcoming chapters. And furthermore, in addition to the computers, we also need to have some improved technologies in lasers and printing, in programmable logic controllers, in materials, in also CNC machining. Otherwise, we will not be able to invent such actually or develop such additive manufacturing systems and machines. This was an example of a printing system. It's, as you see, there are many nozzles here, and at the same time, these nozzles work and you can jet material. So with a single pass of this hat, you can cover the whole, let's say, slice. Yeah, I think we were stopped right at this point. The layers are important in additive manufacturing. We said that about 99% of the time, additive manufacturing systems based on layers. What we do slicing and obtain layers of any products, whether you are printing such a functional object. Again, you need to do slicing and obtain the slices. Again, whether it's a metal part, you need to do, once again, slicing and obtain layers. And the problem with the layers is that if you have such horizontal surfaces, most horizontal surfaces, you will have a kind of a staircase effect. This is actually the biggest problem when you have the slices, layers. So this is called a staircase effect. And if, as I said, horizontal surface, if you have shallow angles there, then you will see this effect clearly. But if it's a vertical surface or it has a very, let's say, steep surface, then it's not easy to see the layers or the staircase effect. But for the horizontal ones, it's a big problem. But here you see, we have an example here, a nice implementation. I think this was out in around 2018 or 17. What they did, this is a conventional FDM printer, fixed line fabrication system. If you follow the conventional, let's say, again, design and fabrication, you'll have such a staircase effect on this almost horizontal surface, which is a very low angle, a shallow angle here. You can easily see these stairs. But once you do a kind of implemented approach, this will be the result. What are they doing is that they are actually moving the nozzle. We didn't discuss the details of extrusion yet, but in extrusion systems, we have nozzles and the temperature of the nozzle is quite high. So what they did is that they move the nozzle into the shape a little bit and try to, let's say, overcome this staircase problem. And as you see, at the end of it, they have a perfect, let's say, surface, which has no staircase effect. We, on the other hand, we also have some layerless method, but these are not the conventional systems. The conventional additive manufacturing systems all have layers. They based on horizontal slices. But if you have multi-axis systems like this one, you cannot easily talk about horizontal slices. For instance, what is this extruder doing here is that I'm not sure, but we can see in the video, probably it's extruding in such a manner. So its slice is kind of a circular, but it can also extrude material in such a way. So this is a multi-axis FDM printer, and this is a commercial product. It's called as 5-axis maker. So we will jump to a different topic now. We discussed the fundamental technologies we need to have in the additive manufacturing systems while developing such systems. Now I will briefly discuss the additive manufacturing process, how we are classifying them. There are different approaches. I will talk about two of them. The first one is the one available on our textbook, FAMS 2D method. And this method actually classifies the additive manufacturing process according to the number of channels they have and the type of material inputs they are using. But obviously, we don't have a single approach. There are many classifications. And as I said, I will be discussing just two of them today. This is a summary of actually FAMS method. We have, as you see on these columns, have the channels. If you have a 1D channel, then that means you have a single head or a single nozzle, single laser, single jetter. You extrude or jet material from a single, let's say, point. So that's why it's called as 1D channel, or you can assume that these are point-wise systems. In addition to that, you may have some numbers of these 1D channels. If it's a laser, then that means we are using two lasers at the same time. And there is, you see, covering the layer. So what do you think, which one is faster in terms of fabrication?
İki tane olan.
Obviously, since if you have two lasers or two extruders, you can cover the whole region in almost half time with respect to the 1D channel. So they are working in parallel and it will take less time. You can also increase this one up to maybe 4 or 5, but things might be complicated, getting complicated. We will see some metal laser systems. They are using 4 of the lasers at the same time. We just increase the covering, increase this process, and decrease the overall fabrication time. And furthermore, we may have an array of 1D channels. Do you remember the printing head I just showed you a moment ago? In that printing head, we had thousands of nozzles on the same line, and this is called an array of 1D channels. And obviously, this one is again much faster than the 1D or 2 times 1D channel, since with a single pass of these nozzles, you can cover the whole layer. Furthermore, we have 2D channels. It's obviously much faster than these, since you don't need to move your actually head. How we do it? And these 2D channels are usually using some kind of lights, let's say projectors. Once you project an image onto that layer, a specific image, your material will be cured or fused together. And this is mostly used with the liquid polymers. We will see some examples. We have a liquid polymer, and this is mostly a thermoset material. Once you reflect that image onto that liquid polymer, due to the levels of light, the polymers will be actually photopolymerized and they will be solidified. Initially, they are liquid, but once you reflect some light on the liquid polymer, they will be polymerized and you will have a solid layer. And the advantage is that since by simply projecting an image, you do the fabrication. So that's why it's much faster than the previous one. In just few seconds, you can be done with that corresponding layer. So it's much faster with respect to 1D channel. These are the columns, actually, how we categorize them, how we classify them. And if you look at the rows, on the row side, we have the materials, the types of materials. If you have liquid polymer, and as I said, this is mostly resin thermoset material. If you use a single laser head, we will discuss the details, but right at this point, I'm not going to give you all the details of the systems, but just know that we have such a classification depending on the material and the type of channel we have. We have different systems. The first one is an SLA system, stereolithography. Actually, the first type of additive manufacturing machinery. They use a single laser channel and they use polymers, liquid polymers. And also we have a variation of this one, very similar to the simplest SLA system. The only difference is that they are using another laser to decrease the fabrication time. Then we have some jetting systems. If you remember the printing hats, jetting hats, they have thousands of nozzles, and this can be done with the help of liquid polymers. And lastly, if you use a projector, a digital light projector, and a liquid polymer, we can have such an additive manufacturing system. It's a trademark, but we'll discuss again the fundamentals later. And in the second row, we have discrete particles, the powders, plastic powders, thermoplastic powders, or metal powders. For instance, this one. This rock is actually fabricated by using metal powders, and you can, I think, see the powders there. It's a very low quality one, but a small part. And we may also have, as I said, not just metal powders, but plastic powders. Different plastics can also be printed with these approaches. What do we need to have again? We may have a single channel laser, or we may have 2 or more channel, or we may have some numbers of, let's say again, jetters, which are jetting the binders, not the material itself. The binders are jetted in the 3D printing technology. It's a trademark, and I will again discuss it probably around 7th or 8th week of the semester. And lastly, this is a very specific process. It's not that common, since it's quite difficult to join these discrete particles in a 2D manner. And for the powders, actually we should follow some types of 1D channels. Then in the third row, we have the molten materials, and they are mostly extrusion-based systems. And we love to use actually single channels, and these days you also have independent dual extruders. I will discuss them. And they can be an example for 2 times 1D channels. And this is a bit low technology. We don't have thermojet anymore. It wasn't successful. It's quite complicated, so people couldn't manage it properly. And again, we don't have a 2D channel option for the molten material. The last one, in the last row, as you see, we have a different form of materials. This time we have solid sheets. So we can have such sheets of paper, sheets of metal. In the discrete particles that can draw them, we have such powders. And in the liquid, we have obviously a liquid polymer. And we don't have 2D channel or 2 times 1D channel versions of the solid sheets. It's not possible. We can only process the solid sheets using a single channel. Any questions, guys, up to this point? Anything you want to point out? Some of you may be familiar with some technologies listed in this table. Okay. So these were types of materials: liquid one, discrete particles, molten materials, or we can use forms of sheets. What about the columns? So it goes like that: 1D, 2 times 1D, again some many times 1D, and then 2D. What about 3D? Can we have such a system? A 3D, for instance, hologram. Can we use it, or how can we use it? Can anyone talk about it? Is it possible to have a 3D shape maybe just in few seconds? What do you think? Is it possible, or how can we do that? Right now, we don't have commercial systems.
Hocam,
Yep.
can we say that casting is a 3D holography?
Yes, but it's not a printing and it's a manufacturing system.
Yes.
You have molten material. You are here. It's casting. It's a different name. It has a different approach totally. But you are somehow right. It's in this column. You have molten material, but you have a mold. Since in additive manufacturing, this is the main difference. We don't use any molds. Artu, do you want to talk?
If we could maybe create a field, for example, magnetic field, and control it really well, we could create 3D shapes.
Then actually you should
maybe we could sinter it.
Material. So what type of material do you want to use?
Maybe we could sinter metallic powders.
So you say you are in the second row, you are around here, right?
Yes.
But how can you do that? Since in sintering, you need to increase the temperature of these powders and join them together. We'll discuss the fundamentals, but here let's say that in sintering operation, if you have two powders, then very similar to powder metallurgy, you increase the temperature up to some intermediate values of melting temperature, then they fuse together and they stay together after that point. But it's quite difficult to do it with just using magnetic forces, since you will also have magnetic forces for the neighboring, let's say, particles, neighboring powders. This is actually the main difficulty. So you may start with a box of powders, and you say that you will have some complicated magnetic systems and then give power properly so that at specific times, different regions, I think, will be sintered together and the other regions will not be sintered. Is that what you are thinking?
Yes, yes.
Okay, nice idea, but it's quite difficult to implement. If you can do that, I think you may be a billionaire. Another approach can we use, any guys?
Hocam, we can use multiple lasers and they can intersect at a point which heats that point more than the surrounding areas.
This is something in my mind. You may use liquid polymers. So you may have a box of, let's say, polymers. As your friend points out, you may have many lasers around at all angles. And by increasing the, let's say, energy of these polymers, you may cure them, you may solidify them, and have different shapes. This might be possible, but as far as I've seen, there was a paper working on these, but I didn't recently check their results, but they are still working on it. But if it's done, if it will be done in near future, then it will be an awesome thing for additive manufacturing, since if you have such a technology, then maybe just in a minute, in some 60 seconds or more than that, in 5 minutes, let's say, you will obtain the final part. And since these days people are mostly criticizing additive manufacturing that it's taking too much time, since they are just considering the fabrication time and they are comparing with injection molding or additive manufacturing, it's obviously much slower. But Once they come up with an invention, I think this will be a great, let's say, movement for additive manufacturing industry. So now we can continue with the rest of the slides. Yes, as I said, we have many classifications. This was a classification in our textbook, FAMS method. And we also have some formal classifications. But the thing is that they are still working on it. We can have a look at it. It's a working item, ASTM, and they are also working with ISO. And these days, they come up with 7 types of additive manufacturing systems. And if you remember, this image was available from 3D-Hubs.com. We have wet polymerization. We have liquid polymers. We use material extrusion. We have solid. We start with solid materials and then liquefy them with the help of some heat. Or in the third approach, we jet material. The fourth one is similar. These two are very similar. This time we are jetting binders, not powder. In the fifth one, this one of the classical approaches. We have powder bed. We spread the powder on the table and then with the help of lasers, we melt them and join them together. Then we have direct energy deposition systems. In these, again, we make use of lasers. We deposit laser and also the powder at the same time. And lastly, as we have seen also in the FAMS table, the sheet metals, we can use sheet lamination approaches. So this is the main classification of standardization from ISO and ASTM. So now let's go into details of some systems. We will start with the first row of FAMS method, the liquid polymers, how we are using them. The first one is object arrays, and I think I can share the web browser. Yes, this is the liquid polymers. This is type of machine. This is their CAM software. Again, as you see, they are using, unfortunately, the STL file format. This is their, as I said, CAM system. They import it, have done some modifications, and then submitted to the. Now you see the printing process. They are using some numbers of jets, and these jets are jetting liquid polymers. While they are jetting, they are also curing this liquid polymer at the same time. You see, they have a light here. So with the help of this light, the polymer is cured and is solidified. These are their materials. They are replacing it. Now the cars are finished and they have some extra material around. So now he's going to remove it and do some post-processing. Like in the design and fabrication pipeline, after you are done with the printing, you need to do some cleaning operations. Cleaning the tray. Now, yes, now with the help of a water jet system, they are removing the support structures. This is a final product. It's a functional product. As you see, the wheels are rotating. This is called B9 Creator System. The video is not that fine, but I'll describe you. Again, this is a CAD software. They do a design and they import it into, again, the CAM software of this special printer. This time, the printer is using actually a kind of a projector, which means that we have a 2D channel, and with the help of this 2D channel, the layers will be cured at a time. We are not moving, we are not sweeping the plane, or we don't have a point-wise curing system. We have a 2D curing approach. Now, we are doing some settings. Layer thicknesses will be set, some exposure times of the projector. Very primitive CAM software, not a complicated one. Yes, this is their system. I also have this one in my lab. Underneath, I'm not sure whether you can see, we have a projector here. This projector is projecting images on the bottom of this vat. And since we have liquid polymer here, once you reflect white, let's say light into that vat, the polymers will be cured. And this is our z-axis. Doing some operations for the next layer. Yes, this is underneath of the printing system. This is projector projecting some white and black regions. White regions will be cured with the help of the light, but the black regions will not be cured. Now they are playing with the focus of the projector, and this is the top side. This is the tail. The part is actually built here. After each layer, it performs such motions to do some cleaning. Not a complicated operation, and here you see the liquid polymers. Now the part is finished. And we will see the part now. The advantage of the system is that its resolution is quite high, and you can have highly complicated and small parts easily. They have some extra polymers. Yes, you see these are not that complete, but some rectangular shapes.
Hocam,
Okay, any questions, guys, about the system, this DLP based system?
hocam,
Yes.
if we were to print a shape with a cavity in it with this system, would it be filled with polymer at the end?
Yep, if you don't have opening, it will be always completely filled. It's not possible to have, let's say, interior properties. Interior features are not possible with DLP technology. We will discuss all these in upcoming, let's say, lectures. But if you have a hole, let's say, then it's possible, and you need to properly remove the resin inside and then maybe do some post-curing operation. There's another system very similar to the previous one. This is much more professional, much faster. Again, they are using a light engine or a projector underneath. This was actually inspired from Terminator 2, but the fundamentals are the same. The main difference is that it's much faster.
Company called Carbon 3D just introduced a totally new kind of 3D printing. They were actually inspired to make it from the movie Terminator 2. Conventional 3D printing involves a printing head that passes over and over across a platform, depositing a thin layer of material each time. And this 3D printing forms an object continuously out of a liquid resin. So what's happening here is you have a bath of liquid resin that solidifies when the light hits it. So the platform dips into this resin, and as it rises up, you have a projector underneath the resin pool that's projecting a series of
Yeah, the main difference of the system with respect to the previous one is that they have a special window and it's oxygen permeable, and they can adjust the amount of oxygen moving into this tank, and with the help of it, they can increase the speed of the process.
sectional images that are in the exact shape of the object you want to make. So as the platform slowly moves upwards, the projector moves through the different images, the different cross sections, and that causes the object to form in the shape you want. Wherever there's ultraviolet light hitting it, that's where the plastic solidifies. So this could be a big deal because it's a lot faster than conventional 3D printers. It works in minutes instead of hours. Right.
This is the conventional FDM type of printer, MakerBot, and as you see, it takes some hours, but in their system,
3D printing is still kind of
Obviously,
a
depending on the
niche
part,
industry.
they can
People use it
produce
to
in
make
some
models or
ways.
prototypes, but if this new 3D printer can be perfected, it could be possible for it to be used to make mass-produced goods.
so we have another, if you remember the fence table, we have the second row. It was for the powders, so discrete particles. This is an example of it. They are using powders. This is their system. And the process is called selective laser sintering. We will discuss the details, but we can now see that we have powders on the table, and with the help of the laser, these powders are sintered together. And with the help of it, we can obtain highly complicated products. And again, in their design and fabrication pipeline, they are doing slicing, obviously. You can see the laser here, how it is curing the, how it is sintering the powders, not curing this time.
CO2 laser traces the cross-section on the material. As the material is heated,
So let me skip some of these. Fundamentally, they have a build chamber. This is their bath. They have powders. They spread the powder at each layer and then join these powders together. So that's why this is a discrete particle system, and they use a single channel, single laser. Here, another one, Z-Corp 3D printer. This is again a particle-based system.
Inspire Z Corporation, a solution from a company whose name is synonymous with innovation, Z Corporation. Now you can create the
Very similar to the previous system. The only difference is that they have multiple channels instead of a single one.
solution
And
for
that's
the most
why
demanding
they can
applications.
easily have some colors since they are jetting material this time instead of using
This all-in-one
lasers.
is the solution you've been
Not as
waiting for.
important since we will spend more time on these in the upcoming chapters. Now I would like to continue with sheet-based, actually solid sheets of materials. The last row of the FAMS method, or the last item in the classification of the ASTM. This is called as laminated object manufacturing. They have sheets of material and then put these sheets on top of each other. It's a simulation. They have sheets of metal, and then with help of laser, we cut these sheets into specific parts. Yes, with help of the roller, they have another layer of sheets. This is a better actually illustration. We have roll of sheet metal here. It's moved on the top of the table, and the parts are actually cut into some regions according to the STL file once again. Again, We will discuss the details of this one, this approach, in the upcoming chapters. We have another type of sheet lamination based system, additive manufacturing system. This time, they are using sheets of composites, let's say, materials. The company is called Impossible Objects.
Impossible Objects technology enables additive manufacturing of fiber-reinforced composites for making production parts. The CAD model is sliced into layers, and each layer is converted into a digital bitmap. Layers are printed onto fiber sheets using a clear
So this is a
fluid.
bit different. They first print these slices on a larger sheet. This is how they do it. This is a composite sheet, and they extrude some kind of special, let's say, resin material onto that sheet so that once they cut them into smaller parts, they can easily be stick together.
And thermal inkjet technology. And a high-precision positioning system guides the inkjet heads. Polymer powder is applied to the fiber sheet, adhering to the printing fluid. Excess powder is removed, leaving behind polymer in the shape of the bitmap. This process is repeated for all of the layers of the part.
So now the layers are all ready, and then they stack them into kind of a special tool, as you see.
Sheets are stacked, heated to melt the polymer.
And after they stack them together, they put it into an oven
Or
try
chemical
to
process.
melt
The uncoated fibers are
resin.
removed, revealing
Now we
the
just
part.
have the composite materials remaining. So it's a nice approach, but I think they weren't much successful. They couldn't sell many of these machines. There's another very primitive type of layer-based system, but let me show you. Again, this is our design. We do some slicing. Thick slices, actually, as you see here. And then they will be manufactured separately. And at the ends, as we have done in the previous case, they will be put onto each other, and the final shape will be obtained. Still, we can consider this one also as an additive manufacturing system. This part, let's consider this part here. This is obviously a subtractive operation, but the rest, the overall approach is an additive manufacturing paradigm.